Today's topic is homotopy lifting property. So the big theorem here is that every covering projection is a vibration. The proof is not at all new in the sense that the fundamental idea involved that we have already seen while studying the computation of the fundamental group of the circle. The exponential map had the property that paths can be lifted and homotopy of paths can also be lifted. That is homotopy path lifting property that we have proved. Whatever idea is there, it is the same idea will work here. The only thing is we are instead of the exponential map explicitly, we are taking any covering projection. And the second thing is instead of homotopy of paths, now we have homotopy of functions from arbitrary spaces. Okay, so you will see that you have to work a little harder, that's all. Okay, start with the covering projection x bar to x. Y is any topological space and H is a homotopy on Y into X. G is a function into X bar, okay, such that when you take P composite G and come back to X, it is H of Y0, the starting map of the homotopy. This is the homotopy lifting data, if you recall. If we have homotopy lifting property, what we have to prove is that you must find a function g from y cross I to x bar, continuous function, such that P composite g is H and this g of y0 must be this little g. That's what we have to find. But path lifting property we have already proved, not homotopy lifting property. Now you fix one point here at a time. Y cross I is a path, right? That can be lifted. Starting point, what do you take? You take g of y. It's given to you already. G of y, such a P composite G of y, H of y0. Y restricted to, H restricted to little y cross I is a path. So that can be lifted already. Do it for all the y. What you get is a function g with this property, but this function may not be continuous as a function from y cross I to x bar. It is continuous whenever you restrict the first coordinate y to a single point. So that much you have already got. And once you require, by this requirement as a function, it is unique. There is no choice, but we have to prove that this very g, whatever we have got, is actually continuous function from y cross I to x bar. Okay. If this is not true, then the theorem will be false. That's all. So we have to prove this one. There is no other choice. You can't. There exists g, but this g has to be this one. So this is the point of path lifting property. Okay. The homotopy of each point here is nothing but a path. So that's what we have to do. So what we have to do is G is continuous as a function from y cross I to I. This is all we have to prove. Okay. Yeah. Given any point in y, we shall first construct an open neighborhood wi of y such that, okay, idea is, suppose you prove a neighborhood open y such that H restricted to, sorry, G restricted to wi cross I is continuous. Then you are done. Because continuity is after all local property. For each neighborhood, if it is true, then you are done. All right. So I am finding a neighborhood wi of y such that there is a partition T0, T1, Tn equal to 1. Okay, partition of the interval with the following property that wi cross Ti to Ti plus 1, H of this, okay, not G. H is a continuous function. H of this one is contained in an evenly covered open subset of X. Okay, so this is what I want to find out. So how do I do that? First of all, choose an evenly covered open subset V little y comma t for each point H of y comma t by continuity of H for every t inside I. Okay, you can choose a neighborhood subset VIT which is evenly covered wherever it goes to, and use the compactness of y cross I to find finitely many of these VITIs to cover H of y cross I. Y cross I is compact, H of y cross I is compact. To choose evenly covered neighborhoods around these points inside X, such that finitely many of them cover the entire path H of y cross I. Everything is inside X now. Okay, once you have done that, choose a partition. There are only finitely many open subsets. So this is the standard argument with Lebesgue number for the interval. So the interval can be divided into finitely many subintervals such that consecutive intervals y of y cross ti plus 1, H of that will go into one of the open sets. Okay. So this is similar to what we have done with the path lifting property also. Even to lift path lifting, we have done this one. Again, using compactness of I. Okay, I is compact now. Okay, y, a neighborhood of I inside X cross I, you get inverse neighborhood, you get a uniform neighborhood. That is the Wallace theorem. You can find an open neighborhood wi comma I, okay, of y such that this H of wi I cross Ti to Ti plus 1 is contained in VI for every. Now take wi is equal to intersection of I into 1 to n wi I. So you have got a uniform y. This is Wallace theorem. Okay, such that partition, okay, and the partition of I as required, such that one single wi cross Ti to Ti plus 1, H of that will be contained inside an evenly covered neighborhood. That was our first aim here. The one single neighborhood of y such that these intervals keep changing consecutively. All of them are contained inside same. Okay, from first we had various intervals here. Next we make them finitely many. And then you took the intersection of these finitely many to get into one single neighborhood of the point y. Okay. Now the hard work is over. So here I am again quoting the same picture that you had while path lifting property for the exponential function. This is your interval, and this is your x here, that's all. X was also interval. So here I'm taking, now you have to think of this as x. Okay, so x is now covered by open y. Y is covered by open subsets wy instead of rectangles like this and so on. But along the y-axis you have subdivisions. Along the the interval, you have subdivisions here. Okay. So this is what I have explained already. So now put w equal to yi. Okay. We shall see that if G restricted to w cross ti, successive application of that, okay, will produce G restricted to w ti plus 1 is a continuous for all I. So what I'm trying to say is, start with on this one you have your function continuous. Okay. Therefore, you get a continuous function along this one, because this whole thing is contained inside a single even neighborhood. So the inverse image makes sense because it is evenly covered neighborhood. By the uniqueness, whatever G you have got already, there is no question. This must be the same thing as that one. So continuity on these parts like this, one by one follows. Because on each of them it is given by an inverse image. Now you have continuity along, say this is G cross some Ti. Insert G cross, Y cross 0 to Y cross Ti. Use that again along these blocks to go to the next stage. So ultimately in finite dimensional stages you will come for the whole thing is continuous. Okay. Continuity on each of them. These are closed subsets of Y cross I after all. I mean, actually open subsets. So finitely many open subsets actually all along this way, but this way it is need not finitely many, because there are Wi's which cover the whole of Y. So on each open subset it is continuous, so whole thing is continuous. Okay, so this part is same as in the case of exponential function and path homotopy lifting. So let us go to some little bit of exercise and so on. What we are going to do in subsequent sections is, this theorem will be applied again and again. Okay, and then we will produce lot of interesting results. The fundamental result is that from any space Y, a homotopy, one of the map can be lifted, the whole entire homotopy can be lifted. The homotopy homotopy lifting property of the covering projection. Okay, this will be used again and again. So let us look at this exercise. Take a covering projection over the space X cross I. Okay, where X is locally path connected, etc. You have to assume, and you can assume path connectivity also. This is, if you restrict P inverse of X cross T at each level, okay, take P inverse of X cross T to X cross T. Okay, this restriction map is a covering projection for each T. Is what you have to show. Remember, if you take arbitrary subsets, the inverse image, okay, full inverse image, then that will be a covering projection. Okay, so this is not a very difficult thing to prove. The point of this one is, all these covering projections will be, in some sense later on, will be same, because x cross t is the same, no? X cross t or x cross s, they are homomorphic to each other, they are copies of x. The above spaces will be also homomorphic to each other in such a way that the projection map, it commutes with that homomorphism. So that will come later. Right now, you have to just say this much, okay? This is the second part. For each t comma s belong to S, show that there are homeomorphisms depending upon t and s, theta ts, p inverse x cross t to p inverse x cross s. This is a homeomorphism. This is identity map. Identity map on x comma t going to x comma s. Okay. This map is x comma t, identity cross identity, whatever. T goes to s, that is the difference here, that's all. So such a diagram is possible. This is what you have to show. Looks crazy, but you don't need anything more than what you have learned. Don't even need homotopy lifting property, just the definition of covariant projections. Okay. Okay, so let's stop here. Thank you.